we will discuss genetic algorithm for real parameters. It is also referred as RGA or real coded genetic algorithm. In this lecture, first we will go through the real coded genetic algorithm RGA. We will understand this algorithm through the working principle, and then we will show the one generation in a graphical illustration. Thereafter, we'll show the case studies from the mechanical engineering domain, and then we will close this session. So let us begin with the real coded GA. So as far as we understand that we use binary coded GA for solving the real parameter optimization problem. In this one, we will be focusing our discussion on real coded GA, RGA. So first question is that we have used binary coded GA in our previous chapter. So what could be the limitations with the binary coded GA? First of all, the binary GA makes the search space discrete, meaning that when we are using the decoded value, for example, 15 or 16, we are actually making our search space discrete. It's because that you remember we discussed about the precision. So based on that precision, we will not get any value in between or less than the precision. So in a way, we are solving for our problem for the particular values of xi's. Second is the problem is called Hamilcliffe problem. Now look at these two binary string. So first binary string, if we decode, it is 16, and the second binary string, if we decode, it is 15. Now, if we are going to use 15 and 16 decoded value, and if we get the value of xi, then we will get the near the neighboring number of xi. But if we look at this binary string, they are totally different. For example, the first binary string, I have to mutate each and every bit, then only I will get the second bit. So let us assume that the optima is lying at 10000, the first string, but our GA has reached 01111. But in the neighboring xi, we are close to the minima, but for a binary coded GA, it has to convert every bit in this second string, then only we'll get the first string, which we have assumed it is a minima. So this problem is called Hamilcliffe problem, in which the real number are in neighbors, but in the binary string, they are very far from each other. Third problem with a binary coded GA is the arbitrary precision is impossible due to the fixed length coding. So we remember that we started with the precision. We used the binary string length of 5 and we found the precision. When we increase the precision to 0.01, the length increased to 10. Now suppose if we want 10 to the power minus 8 or 10 to the power minus 10, then we can assume or we can understand that the binary string length will be huge. So a very large binary string a computer cannot handle. So therefore we are limited with the precision. So having those disadvantages or limitation of a binary coded GA, we have some algorithm called real parameter evolutionary algorithm. So you remember that evolutionary algorithm was a part of computational intelligence in our previous chapter. And inside evolutionary algorithm, we have one of the algorithm called genetic algorithm. So what in these real parameter algorithm, the decision variables are coded directly instead of a binary string. However, we have to think how we are going to do crossover and mutation. Selection operator remains the same. So this we will discuss with our example. So the things will be more clear to us. So this flowchart is familiar to us. Why? Because this flowchart is the same as the binary coded GA. Now we are going to make the changes at two places. That is, when we are generating the random values of x1, x2 variable, so that will be in a real number. But in binary coded GA, it was in a binary string like 0101 pattern. So first change should be done in the number. So the variables will be represented directly in a real numbers. Second is in the variation, meaning that we have to perform crossover and mutation. Since we are dealing with the real numbers, we cannot use the concept, or we cannot use directly the binary string since it is not available with us. So we have to change crossover and mutation uh, for converting the genetic algorithm to real coded GA. The rest of the things will remain the same that we are going to understand with an example. Looking at this algorithmic representation, so we will be following the steps which are given here. Solution representation in real number, that is genetics. Step 2 is always our input. For example, generation counter and maximum allowed generation. Then we initialize the random population PT, and thereafter we evaluate. So evaluate means we are going to evaluate objective function, constraints, and assign fitness. After going through the binary coded GA lecture, so we understand what we mean by assigning fitness. Now we are inside the loop. We do selection, that is survival of the fittest. We do variation, that is crossover and mutation. Then we get offspring population called Q. Then we are going to evaluate it, and then the survival stage where we have P and a Q, and we are going to select the best N solutions. So let us take the same example which we have solved earlier, but now this example will be solved using real coded GA. So as we understood, we need to design a can which should contain at least 200 milliliter of water, and the objective function is to minimize the cost of the material. So as we remember, diameter and height were the variables. So we can write our objective function as the surface area multiplied by the factor C, which is cost. And then we have a volume which should be greater than 300. And then diameter and height. Again, we are taking diameter and height between 0 to 31, but it will take the real number. So let us, as we remember, we have to start with the initial random population. So we chose the population size, that is capital N, is equals to 6. So we have given the index as 1, 2, 3, 4, 5, 6, and the diameter and a height within the range of D and H, we generated a random number. So these random numbers are generated within the range. So as you can see, these are the diameter and just as a reminder, GA begins with a random set of points instead of one, as in classical or say gradient based optimization method. Once we generate the population, which is a parent population, now we have to evaluate it. So we understand that we will be having diameter and a height, that is a solution number 1. Putting into the values into the objective function, we get the value of F, 35.97. Thereafter, for solution 1, we find the constraint. This is coming out to be 933.68, which is bigger than 300. So it's a feasible solution. So the fitness of this solution is the same as the objective function value. So the capital F DH is equal to 35.97. So as we discussed earlier, the fitness is the objective function value plus penalty if the solution is infeasible. So let us convert this particular inequality into greater than or equal to 0. So GDH minus 300, that should be greater than or equals to 0. So this is our standard form of writing the constraint. Now let us take the solution number 2. We calculate the objective function as 19.94. Now let us calculate the constraints now, which is 235.73. It is smaller than 300, so we know the solution is infeasible. So here we are going to assign a penalty using one of the method called penalty parameter less approach. What is that? The fitness of a solution X is equals to the function value if the solution is feasible. Otherwise, we are adding one term called Fmax. We will see what is that, plus. Now for all inequality constraints, we have this bracket operator, and then we are taking a mod. Since we are assuming that this particular approach we are using for minimization problem. So we are making a mod so that all constraint violation will be added here. This we will do for all inequality constraint, plus we have equality constraint, and we are taking the mod. So every constraint violation which is in GJ or HK, all constraint violation will be added to Fmax. Now question is, what is Fmax? Fmax is the objective function value of the worst feasible solution in the population. So we'll check how we can find this. Bracket operator is known to us. Now this is the population member, 6 members we started. We have diameter and height randomly created. We calculated the function value in the third column and the constraint in the last column. Now looking at the value of the constraint, we can see solution 2 and 6 are infeasible, and solution 1, 3, 4 and 5 are feasible solution. So the feasible solution are shown in the green color. Now let us read again. Fmax is the objective function value of the worst feasible solution in the population. So currently we have 4 feasible solutions, which is 1, 3, 4 and a 5. Let us look their objective function value. So solution 1, 35.97, solution 3, 68.54, solution 4, 174.84, and solution 5, 93.19. Since we are solving a minimization problem, among these 4 solutions or 4 feasible solutions, so among these 4 feasible solutions, the worst feasible solution is solution number 4, which has the maximum fitness value, which is 174.84. So Fmax, as you can see at the bottom, Fmax will become 174.84. Again, please note that when we are calculating Fmax, we will be only looking at the feasible solutions. So which are 1, 3, 4 and 5. We will look their objective function value, and among them, which is having the Fmax value, which is having the maximum function value, that will become Fmax. So the same table is regenerated. We have a solution index in column 1, diameter height in column number 2, function value in the column number 3, and the constraint value in column number 4. Now in the 5 we have a fitness. Since solution 1 is feasible, so we remember that fitness is equals to the objective function. Look at the solution number 2. So solution number 2, since it is infeasible, so what we have to do? Let us go back. We have to do Fmax plus constraint violation. What is Fmax? 174.84 plus what is constraint violation? Constraint violation is 64.24 for solution number 2. So we have to add them. So this minus will become plus because we have to take a mod, and you will get the fitness as 239.11. Similarly, the solution number 3, 4 and 5, they are feasible. So that's why the objective function value and the fitness value are the same. Coming to solution number 6, I'm going back here. Fmax is given to us. This plus 202.14 should be the fitness value of solution 6, and that's why it is 381.96. Now once we calculated the fitness, we have to check the termination condition. Since it is the first generation, we will move ahead. So we remember that we use the binary tournament selection operator. Now, when we started this particular lecture, after going through the limitations of binary coded GA, we mentioned that there is no need to change the selection operator. Why? It's only because the selection operator works on the fitness. And you remember that in previous slide, we already calculated the fitness. So since fitness for each solution is available, we don't need any change in the tournament selection. So just as a recap, selection operator is used to identify good good solutions and eliminate bad solution in the population. For performing this binary two-element selection, we are making a pair of two solutions randomly. So 2, 4 will compete, 1, 3 will compete, and 5, 6 will compete. When 2 and 4 will compete, index 4 is the winner. Looking at their fitness, we can see that solution 4 is having a less fitness for a minimization problem. Similarly, we can compare 1 and a 3, index 1 will be the winner. 5 and a 6, index 5 will be the winner. Now 4, 1 and 5 are selected. These are three solutions. And to make a number of solution to 6, which was the which is n equals to 6, then we have to perform one more time this binary two-element selection. So now randomly we are picking 3 and a 1, 6 and a 2, and 5 and a 4. So when we pick 3 and a 1, index 1 will be the winner. 6 and a 2, index 2 is the winner, and 5 and a 4, index 5 is the winner. So the properties of the binary two-element selection for the best solution in the population, which will get 2 copy, and the worst solution in the population, which will get 0 copy, that those properties will remain the same here as well. Now we are moving ahead towards crossover. So we perform selection. Now we will be performing crossover. Now we remember that the purpose of the crossover is to create new solution. Now here we have this mating pool. So this mating pool means we are including new index. So 4, 1, 5, 1, 2, 5 are the solution selected from the previous slide. As you can see, same sequence we have taken 4, 1, 5, 1, 2, 5, right? So we have arranged the solution. Now we are giving them an index as 1, 2, 3, 4, 5, and 6. Now the crossover, we are going to learn about one of the crossover operator that is performed between the two solution. So we are going to choose two solutions randomly. Say for example, as per the new index, we will be selecting 1 and 4 and then perform crossover, then 3 and a 5, then perform crossover, then 6 and a 2, and then perform crossover. These are some values. Probability of a crossover 0.9, eta c equals to 15. These are the some user defined parameters. So let us understand the crossover operator. Now, as we remember that in binary coded GA, we have a binary string and we choose one vertical line that is a crossover side and then we swap the tail. But here it is not possible. So we need some structural change in the crossover operator. So here now we are going to discuss one of the crossover operators that is called SBX, simulated binary crossover operator. I'm discussing this crossover operator because still it is one of the famous crossover operator for solving real parameter problems. So here we use probability distribution P beta I, and you can see the functions which depend on the beta I value. In order to calculate the beta I value, we are going to integrate this probability distribution from minus infinite to plus infinite, and then we can get it. Now, as you have to understand that when we have to find this area under the curve, we always equate this area under the curve to the when we are finding from minus infinite to plus infinite for say variable xi. So the area should always be 1. So this we can correlate with the random number ui. So when we are integrating from say minus infinite to say to some beta value, then this should be equals to the random number. So based on that, you can look at the beta value is given as 2 times of ui. Ui is a random number 0 and a 1, which will be given by the computer. And this particular factor has the power 1 divided by eta c plus 1. Now eta c is the user defined factor which is needed for the SBX operator, and we have to choose it. So if I go back, so we have chosen eta c is 15 at the bottom, you can see. Right, now looking at this beta value, the offspring, now xi1t means xi ith variable, 1 means first solution, t plus 1 means it's going to be an offspring solution, is equals to 0.5, 1 plus beta xi1t plus 1 minus beta xi 2t. What is the second solution? Now you just see the change only in plus and a minus. Now 1 minus beta xi 1t plus 1 plus beta xi 2t. So these two solutions to of a spring are symmetric about solution in order to avoid biasness toward any particular parent solution in a single crossover operation. So this is the property of this particular crossover operator. So as of now, I'm not going into the proof of this particular crossover operator. What we can understand is as and when we have to generate the offspring, we need the value of a beta. This beta depends on the random number ui. So we are calculating, we just generate a random number by a computer, feed into it, it will give me beta, and that directly beta I can use it to calculate two offspring solution. And xi, as I told you, we perform crossover variable wise, meaning that if I'm choosing the first variable x1, then there is a crossover between two solution for x1 variable only. There are certain properties with the SBX operator as well. Now you look at this particular curve. Now when eta c equal to 2, it's a solid line. When eta c equals to 5, it's a dashed line. What we can observe is if suppose we have two parent solution as 2 and a 5. Now if we increase the eta c value, then what will happen that the area under the curve will remain the same for both solid line as well as dashed line. But since eta is increased, so you can see the peak is going above. So what it suggests that if we increase the value of eta c, then the offspring will be created closer to the parent, meaning that the offspring solution close to 2 will be generated and another offspring solution will be generated closer to solution number 5. Another property, as we have discussed, if we make a difference between the offspring solution, this is equals to beta I times of the parent solution. And this is another property which is quite interesting. Say suppose we have two solution 2 and a 5 which are currently far. When we generate the offspring solution using SBX operator, now as you can see in the figure on the left hand side, offspring are also far. Now if the offspring, if the parent solution are 2 and a 3, not even 3, 2 and another solution which is in the black dot, since they are very close, then the offspring solutions are also very close. So it means that as we remember that initially we have to explore the search space, and once we locate that this is the region where the minima, then other solution will try to converge there. So this crossover operator is adaptive. Why? Because initially when the solutions are far, that is as per the second left hand figure, then the offspring solutions will be generated far as with respect to the parent solution. But when we are converging to the optimum solution, that is after certain generation, the figure on the right hand side, because the parent can be closer to each other, so the offspring solution will be also closer to the parent solution. So let us perform some hand calculation. So we remember that we picked solution 1 and 4 randomly. So solution 1 diameter and height are given, and solution 4 diameter and height are given. Now, since the random number is 0.42, so this we created and we found that it is smaller than PC, which is 0.9 in our previous slide though. So we are going to perform the crossover. So let us perform the crossover on the D first. So as you remember, I told you that the crossover should be done variable wise. So we have chosen D first. So let the random number UI is this. Using UI, we can calculate the beta I value. Now we are going to include this beta I value. Since two solutions we have chosen, now you can see 0.5 times of 1 plus beta xi 1t plus 1 minus beta xi 2t. Now what we are going to do is we are putting the value as 0.5 1 plus 0.991, which is beta value, into 8.48. Now look at this, 8.48 is the first. Then we have 1 minus beta 23.96. So this is going to give me D1 value, which is 8.55. Similarly, D2 value, is 23.49. Now same procedure I have to follow. It's a very straightforward that once we calculated UI, we will find beta I, then we have to just put into the formula. So we are going to do the same thing for H. So let UI is 0.94 and beta I, calculated beta I is 1.142. By putting into the formula, same formula, we are going to get H1 is 15.97 and H2 will be 25.15. So what are these two solutions? D1 and H1 will become first solution and D2 and H2 will become the second solution. So these are the solutions which we get after crossover. Now we are picking solution number 3 and a 5 and let the random number is 0.93. Since it is greater than probability of crossover, we do not perform the crossover. So in this case, what we will do is we will just copy solution 3 and 5 as it is. Now pick 6 and a 2 crossover. And since the random number is 0.19, which is smaller than PC, we perform the crossover operator. Now, as we remember, we will take D first. Suppose UI for D is 0.75 and for H UI is 0.13. So that is going to give me the new D and H values. So two new solutions will be created. So we remember that we perform the crossover between 4 and 1. So look at the column number 1. Diameter and height are given. Of a spring are generated as we have discussed in the previous slide. We are giving a new index as 1 and a 2. Fitness values are given. The constraint value is given. Both of them are feasible. And the fitness value. So fitness value we generally calculate after finding Fmax. So we will discuss the last column later. So here, so 3 and a 5 solution, we remember that we did not perform the crossover. So these solutions are copied. You can see the yellow one that they have the same, offspring has the same D and H value. Now 6 and a 2 generated another set of offspring solutions. Now we remember that we have to find which are the feasible solution. Now in this case, if I look at first, second, third, fourth, fifth, sixth. If I look at the sixth column, it shows me the value of G minus 300. So the solution 1, 2, 3, and then 5 and a 6. They are feasible solution. Solution 4, as per the new index, it is infeasible. So for feasible solution, we know that the fitness is the same as the function value. So you can find it out. Now for the fitness of infeasible solution, I have to find Fmax. What is Fmax? Now I'm looking at the function value of solution 1, 2, 3, 5 and a 6. Among them, we can find that the worst feasible solution is solution number 2, having a function value 176.88. So as you can see on the last column where I am showing you the fitness, Fmax is given as 176.53. So what will be the fitness of this infeasible solution number 4? 176.53 plus 64.27. So the fitness is given here. So the observation here is when we started in the initial population, the one solution having the best fitness 35.97. And after the crossover, we get one solution, which is the last solution. The fitness value is 33, which is even better than the solution in the initial population. So we have the same observation that the crossover can generate good and bad solution. Bad solution will be die out or it will be deleted in further generation, and good solution will get the multiple copies. As we have discussed earlier, since the crossover is performed on the two solutions which survived the tournament selection, then most likely the new solution will get the good traits, and that's why few crossover operator will generate better solution than the parent solution. After crossover, we remember that we perform mutation. Purpose of the mutation is again to create new solution, but with a small probability. So we are going to understand this polynomial mutation. This polynomial mutation says that the new solution yi is equals to xi 1t plus 1. So this is the solution generated by the crossover plus xi upper minus xi lower multiplied by delta. How we are going to find the delta? So we are taking the probability distribution, as you can see, which is a nonlinear distribution, and we are we are integrating this probability distribution and equating with a random number Ri. So Ri is a random number. So delta I can be calculated with respect to the random number Ri. So both crossover and mutation, these SBX operator and polynomial mutation operator, both of them are stochastic in nature because both of them involve random number. In SPX, random number was represented by UI, lying between 0 to 1. In polynomial mutation, random number is represented by Ri. It is lying between 0 to 1. So based on the random number is smaller than 0.5, we are going to use the this equation, first equation. If Ri is greater than 0.5, we are going to use the second equation. So now let us perform some hand calculation here. Let the random number for performing mutation on each new solution R. So we generated the set of random number and eta m. So go back here. So here you can see the delta I again depend on the eta m. Eta m is a user defined parameter and we have to fix it. So here we chose eta m equals to 20. So let us take the solution number 1. Since the random number is smaller than, so random number you can see on the top line. So first random number is 0.03. So we use the same number in the second bullet. 0.03 is smaller than probability of mutation, which is 0.1. We are going to perform the mutation. So we created a random number Ri. So computer generated this random number. With the help of that, delta is minus 0.021. By putting into the formula. So again, we will be doing this a variable by wise. So let us take the D first. So putting into the formula, we get 7.99. Similarly, we generated the Ri for the height h 0.1. Delta I is minus 0.074. And then we get a new h by putting the values and we get 13.68. So the new solution after mutation is 7.90 and 13.68. Now solution number 2, the random number 0.59 is greater than PM. We do not perform mutation, we copy it. Similarly, solution 3, 0.38 is greater than 0.1. We do not perform mutation, we just copy it. Solution 4, the random number is 0.01, which is smaller than probability of mutation. We are going to perform it. So as we remember, we are generating the Ri for diameter. Similarly, Ri for the h. So the Ri are given. And then we can calculate delta I value for the diameter and then height. We can get a new solution as given here. Number 5, again, the random number is greater than PM. We do not perform the mutation, we copy it. And for solution 6, since the random number is smaller than PM, we perform the mutation. So again, we are generating random number Ri for diameter, another random number for height. We get a new solution after mutation. So here we have these 1, 2, 3, 4, 5, 6. These are our solutions. We have a diameter and a height. These are the diameter and height after crossover. This is offspring. So the yellow portion in the third column means we are not performing any mutation. Rest of the solution we are performing. So basically solution 1, 4 and 6 we perform the mutation. Their values are written. Their function value is written. Their constraint is written. Now thereafter then we have to find is there an infeasible solution? So we found solution number 4 is the infeasible solution. Now as we remember, for feasible solution, the fitness is the same as the objective function, but for the infeasible solution, we have to find Fmax. Now, looking at their function value of the feasible solutions only, solution 2 has the worst fit function value. So that's why in the last column, we can see Fmax is 176.88, and the fitness of the infeasible solution number 4 is 176.88 plus 179.99, which is 356.87. So we get the function fitness value. Now there are certain observations. We started with the initial population in which the best solution was having a fitness value 35.97. After crossover, we get a one solution which is having the best fitness 33.23. And after mutation, we get another good solution which has having the fitness 26.35, which is the best as of now. So what we can understand, mutation can create good as well as bad solutions. Good solution will be emphasized, bad solution will be deleted. So before we proceed further, I just give one comment here that in crossover and mutation, I'm showing you the calculation for the objective function calculation, constraint, as well as Fmax. Here we have to note that when we perform crossover and mutation, we don't calculate the function or fitness value because it is not needed. Because as you have understood, the functioning of the crossover and mutation, everything depends on the random number. If random number is smaller than probability of crossover or mutation, we are going to perform it. Then another random number will help us to calculate beta or a delta value. So in the crossover and mutation, we don't need to calculate the function value, the constraint, and the fitness. Here I'm showing just to as a representation purpose so that you can understand that the crossover and mutation can even generate good solution than the parent solution. Now we are at the last stage. So as we remember, survival, where we have parent population and the offspring population. So one of the strategy is the mu plus lambda strategy, meaning that we are going to combine offspring as well as parent population. This we did it in a binary coded GA as well. So the parent population, as you can see on the left hand table, is given. Similarly, the offspring population, which is given on the right hand side. Here, solutions, their diameter and height and their fitness are given. Now you remember that we discussed that other than the crossover and mutation, we don't have to change anything. Here also we don't have to change. Why? Because our survival depends on the fitness value. Fitness value we have to calculate and then we can do it. So how we can do it? I will be combining. So 6 plus 6, 12 solution. It is a minimization problem. So I can sort these solutions based on their fitness value. So we remember, so if I am going to sort in an ascending order, so I know that minimum value is corresponding to solution 6, which is 26.35, followed by solution number 1 in offspring, which is 28.43. Then we have a parent 1 solution, which is 35.97. So one by one, I'm going to copy 6 solution and you can see the solution selected for the next generation. So we are giving an index like 1, 2, 3, 4, 5, 6. Look at the fitness 26, 28, 35, 68, 93, 98. So this fitness is already arranged in an ascending order. So in the previous step, we combined 6 plus 6, 12. Then we sorted them in an ascending order and we chose the top 6 solutions for the next generation. Thereafter, we check the generation counter, it increased by 1, and then since it is not met, we will be performing binary tournament selection, then thereafter crossover and mutation. We will be working inside the loop till the termination condition is satisfied. So again, we have a recap of this. So this is what we have the flowchart of a real coded GA, and as per our understanding, we generated the initial population, means the solution in the real number, evaluate and assign fitness. So we understood one fitness called parameter less approach. Thereafter, we have a termination condition. On the right hand side, yes, we perform binary tournament selection. And under variation, we have SBX crossover and polynomial mutation. Since we generated new population Q, we assign the fitness. Then we have the survivor stage, which we discussed just now. And then we will be moving inside the loop until the termination condition gets satisfied. Now let us understand the same can problem graphically. So here the solid line is nothing but the constraint line. So below that is the solution which is invisible, and the blue dots are represented the initial population. So we have 6 solutions now. We are calculated the fitness, and then we have to perform the binary tournament selection. Now you can see these 2 red dots. This means these solution get 2 copies. Other red dots are selected, but the blue circle without a color, these are the solution which are deleted. So these red dots will make a mating pool for crossover. Now for in crossover operator, we remember that we select 2 solution and apply SBX crossover operator. So these black dots, you can see these are the solutions which are generated after crossover operator. Thereafter, we perform the mutation. So this mutation means these magenta color or a pink color points, we are using it. So these are the solutions which we generated after mutation. And then we have to combine. So these are the combined solutions. So initial population means the parent population as well as offspring population are shown here. Then we are going to select the best solution. So as we can understand, these red dots on the right hand side, these are the solutions which we selected. So so as compared to the initial population, you can see that the 3 solutions are deleted, and these solutions which are red in color, these solutions are selected. Now what we can understand from this, that in one generation, these red dots are moving towards the constraint boundary where the optima is lying. And if we run our genetic algorithm for a few more generation, so solution will be converging towards the optimal solution. Now let us discuss the case studies. First case study is the welded beam problem. In this particular problem, we have vertical bar and has a horizontal bar. In this horizontal bar, the force is applied. We have to decide what should be the width and T, the thickness of this. And these 2 beams are welded together, and the weld material is given as length L and H. So the problem is defined as we want to minimize the cost of the weld subjected to. We have various stresses, one constraint on B minus H, and we have a one constraint on PC, that is the force. The H and B are given at the range or the upper and lower limits. Similarly, L and T, the lower and upper limits are given. The formulas are given at the bottom. What you can see that in this particular problem, the equations are highly nonlinear, and this formulation is made using 4 decision variable, and we have 4 constraints. So when we use GA with 100 population, 0.9 probability crossover, SBX 15, 200 generation, probability of mutation 0.1, and eta M20, we get the optimal cost as 2.873, meaning that this is the solution which we get. As of now, this is the best solution which we found from the literature. Look at the constraint value. First constraint 13, second constraint is a big value. Third constraint is 1.56 10 to the power minus 4. This means the third constraint is active and rest of the constraints are inactive at the current point. What is the point? H is 0.29, B is 0.29, L is 3.9, and T is 9.98. So this is the optimal solution for the welded beam problem. Now there is another problem called design of helical compressive spring. In this case, we want to minimize the volume of this. This problem is subjected to various constraints. The difficult part of this is that we have 3 variables and 8 constraints. These 3 variables, we have n, which is the number of turn, is an integer value. Diameter, small d, is a real number, and capital D is a mean coil diameter. So here the capital D is a real number, capital N is the integer number, and small d is a non-equispace values, means it's a discrete. So it's a multi-variable problem which is difficult to solve. Some input parameters are given for solving this particular problem, as well as the small d values are given. This means that the optimization algorithm should take these values. It cannot take other than that value. And that's why we called d is a discrete variable for us. When we run this GA with 100 population, 200 generation, probability of crossover 0.9, probability of mutation 0.1, SBX operator, eta C for SBX is 15, eta M for polynomial mutation 20. We get this optimal solution, which is the best so far in the literature. Look at the constraint value. Now constraint 2 is quite close to 1, close to 0. Similarly, 1, 2, 3, 4, 5, 6. Sixth constraint is the active constraint in the given problem. What is the optimal solution? N is 8, D is 0.28, and diameter capital D is 1.42. Now let me take the last case study, which is a milling process parameter optimization problem. In this case, we have a block of a material, and that block of a material has to be converted into the design which is shown right now. For converting the block of a material in this design, we need 5 milling operation. So therefore, the problem is stated as we want to minimize the cost of the machining. Subjected to, we have 4 constraints. We have 10 real variables and 4 constraints for the given problem. So here you can see the unit cost CU is given in terms. Now looking at this equation, we can see it's a nonlinear equation. Similarly, there are other constant factor like C5, K1i, K2i, C1, C4i, etc. All of them are given here. Putting the values, we'll get those values to calculate the objective function as well as constraints. There are 10 variables, so we remember that we have 5 milling operation. For each milling operation, there are 2 variables, that is speed, which is represented as capital V, and feed, which is represented as a small f. So 5 milling operation, 2 variable means 5 into 2, 10 variables. So these are the milling process parameter. Again, I'm showing you the list of the constant parameter that are needed to solve the given problem. These are the required data for the milling parameter optimization problem. So we have operations, we have tools, some constants are given to us. There is other tool data for the milling where tool types, quality, CLZ, price, SD, helix angle, other parameters are given. All of them are needed for solving the given problem. So we solve this problem using GA, basically real coded GA, 100 population, 1000 generation, probability of crossover is 0.9, probability of mutation is 0.1, eta C 15, eta M 20. Now for this particular problem, the handbook solution is given, which says that the cost is 18.36. We also use method of feasible direction that is also given in the literature. It found the optimal solution with the optimal cost 11.35. But genetic algorithm gave us 10.86. So you remember that we said that for genetic algorithm, we do not have a proof. But in the literature, genetic algorithm has been used for many real world problems. And we found that it is the effective algorithm to find the best known solution for the given problem, as it is also evident from the current example. So now we have come to the closure of this particular chapter. So in this chapter, our main focus was to understand the real coded GA, since there are many problems in engineering optimization which have the real numbers. So those variables should be represented as a real number. So therefore, we understand this real coded GA. We understand through the same flow chart and algorithm as similar to the binary coded GA. We have understood the fitness evaluation and constraint handling through parameter-less approach. The binary tournament selection we discussed one more time. The 2 new addition is the SPX crossover operator and polynomial mutation. And we understand that when we are making the real coded GA, only we have to think about the crossover and mutation operator. Uh, why? Because that has to be work on the real number. The rest of the operators such as binary, tournament selection, survival of the fittest, all of them need the fitness value only. Then we perform this hand calculation for the CAN design problem. We understand each and everything by solving the CAN design problem for one generation. And we showed the graphically the CAN problem. Thereafter, we discussed three practical optimization problems from the domain of mechanical engineering. The main objective was these problems, we don't know where is the optima, but as of now, GA and other evolutionary algorithm shows the best solution so far in the literature. So with this understanding on binary coded and the real coded genetic algorithm, I'm finishing all the chapters for this particular course. So wish you good luck, everyone. Thank you very much.